Welcome everyone. So in the last lecture, we looked at the Raychaudhuri equation. We did not go through the items. We just said that this is important to calculate singularities. Singularities happen at the center of a black hole. Singularity is a situation where volume becomes zero or undefined and all equations break down. And Raychaudhuri equation is important, and the singularity happens at the Big Bang. We talked about that, and but we didn't go too much detail because that was the introduction. And today we are going to start doing some background material needed to understand the Raychaudhuri equation. So we will be starting doing some kind of a general overview of Einstein's field equations. So before Einstein, that there was, the Newton's theory, where you have the sun and you have the planet, and there was some kind of a force, gravitational force, and the planets were going around. You have the Kepler's laws and all that, but this didn't really work. There were problems with it. So we all know the story. Einstein came up with his equation. But let me digress a little. One time, I went with my daughter to a science fair. And in the science fair, there was a sun like this hanging from the ceiling. And then there were planets hanging from the ceiling. And these strings were very small, and you could not barely see them. A child will not notice them because an adult could see them. So my child asked me, "Where are the tracks, Daddy?" Because they're supposed to go on tracks, like in a train tracks. You see these train sets, but there are no tracks. But I told her, well, there are no tracks, but if you look carefully, there are strings. So these things are attached from the strings. And she goes, yeah. But then I started thinking, in fact, there are tracks. They're called geodesics. In real planets. Our Earth goes on a geodesic. There are tracks. The Earth doesn't go haphazardly like a drunkard man. It goes in an orderly manner around the sun on a track. And that track is called a geodesic. And geodesic is calculated using Einstein's field equations. So basically what you have, we have tracks like that. And the shape of this track can be calculated using Einstein's field equations. So there are tracks. And how these tracks are calculated. Now, according to Einstein, I'm not going to go too much detail. This is the Einstein field equation, or its equations, because these values, these are matrices. This is a metric. These two are matrices. This is a scalar and this is a value. So this side, the right hand side of this equation represents the mass. Represent the mass of these masses. This T is called stress energy tensor. Energy and mass are the same thing. G is the gravitational constant and C is the speed of light. So if you know the mass, you could calculate this side, because T can be calculated using the mass. Okay, so this side is the mass. And this term is the cosmological constant. For like solar system and small scale stuff, we could ignore that. This number comes into play when we are talking cosmology, where universe, where 1,000 million light years of distances. For small things, solar system or stars, we could ignore this term. So this whole term becomes zero. And then this R is the Ricci scalar and this R is the Ricci tensor. These represent the curvature of space. So this side is the mass, this side is the curvature of the space-time actually, and this is the metric tensor. The metric tensor is some kind of a way to measure this space-time structure. So we need to have a way to measure these grids. These grids are fictional, they don't exist. But we need to have some way of measuring them. And that's our ruler. That's our ruler, that's called the metric tensor. And so R is a Ricci scalar, R mu nu is the Ricci tensor. Riemannian tensor is simplified to Ricci tensor. And so this side gives the curvature of the space-time, and this side do the mass. So if you know the mass, you could find the curvature, and if you know the curvature or the movement of these planets, then we could calculate the mass. Actually, this was done to, we see this is the center of our galaxy. These S1, S2, S12, S14 are stars. S2 is a star which is 14 times heavier than our sun. And it goes at a speed of 7,500 kilometers per second. It means it covers from New York to London distance in a second. Now, our Earth goes around the sun at just 30 kilometers per second. That's the speed of our Earth around the sun. But this star goes around something here which we don't know, we cannot see that, at 7,500 kilometers per second. So who the hell out here take this star which is 14 times the mass of our sun and whip it at this speed, just 3% of the speed of light, and you can calculate, if you know this trajectory, then you can calculate the mass at the center here, and it comes up to be 4 million times the mass of our sun as a central black hole at the middle of our galaxy. And there's another better picture, and this is demonstrations. So in this lecture, next lecture we are going to find these tracks, equations for the track, the geodesic equation. That's for the next lecture. But for today, all what you have to know is Einstein's field equation. R. These two R's gives the curvature. Ricci tensor, Ricci scalar. This G mu nu gives the metric or the measuring yard, measuring stick. This is the cosmological constant. For most situations, this term is 0. And T is dependent upon the mass. So if you know the mass, you could find the curvature of space-time. And if you have the trajectory and the curvature of space-time, then you could find the mass, like the way we did in central black hole. So the next lecture, we will talk about the geodesic. Thank you very much for listening.